Okay, so welcome to this doubt session. Yeah, Vishwas, please go ahead.
Yeah. So, sir, I was asking like when we worked out objective quantities in lecture 27. So there basically two kinds of rotations were coming. One Q, which is like global rigid rotation, and R is like local rigid rotation. And wherever Q into R we are finding, we are writing that as say Q star or uh, something like that. So, but both are rotations. Difference between that we understand that one is local line element, understand another is global. But when they multiply, what will that quantity be, sir? I mean, whether how to visualize that?
So that
Because
could be,
most of the quantities that is coming like say for objectivity of when f equals to ru and we are doing so
yes,
there also q into r will come in f
correct,
star.
correct. So in F star, so you have a new F star, no?
Yes, sir.
So F star is then Q into R into U. And this F star independently should have been R star into U star, right? So if you
Yeah.
compare, and the fact that polar decomposition is unique, that implies this part must be R star and this part must be U star. So R star is therefore Q into R. So although Q is a global rotation and big R is local rotation, but the product is the new local rotation. That's why it is R star.
Okay.
Yeah.
But both matrices will have different entries and it can come out like that. It will act as a local rotation only. Global is getting killed. I mean, global rotation is getting killed.
Yes, yes, it will be because you see it is R star, you understand that it has to be local rotation, right?
Yes, sir. Okay. Because it is unique.
Yes.
Okay. Okay.
Right.
Then, sir, just one small clarification. Lecture 27 can be open.
Yeah, yeah, sure.
So here in last part, sir, we are working this spin tensor, whether it is objective or not. So there,
Okay.
W star equals to little above. W star equals to Q into Q dot into Q transpose plus QW Q transpose should come, no, sir. There only
Okay.
W is coming on right side. I think there should be QW Q transpose.
Okay.
When
Uh,
like we can come from that L expression only, like
that's
L
true.
full expression is there.
I agree with that. So it should have been QWQ transpose. So thanks
Correct,
for
QW Q
pointing to
transpose.
this mistake. You're right.
Okay. And how we can arrive is I think L we can write it as D plus W and then
Yes.
symmetric and non-symmetric part we can separate
Correct.
out.
Correct. Correct.
Okay, sir.
Okay. Very good.
Now next is like sir, if A dot is objective, like A
Yeah.
dot, our material time derivative, then
Yes.
there can be two way because normally A dot is not objective. In general, A dot is not objective.
That is
But
true.
if we want it to get objective, then whether we can think of some rotation tensor Q which is not changing with time, then Q dot may be 0, then we can get that A dot also will be objective. Or we have to put restriction on A, like if we want that A dot should be objective,
Yeah.
then
So
what
you'll
could
have
be
to
the
put,
possibilities?
you can't put restriction on Q because for to check objectivity, Q, it has to be checked for Q which are dependent on time. So you cannot put restriction on Q.
Okay, Q in general we cannot put any restriction.
Yes, you can't put any restriction, but yeah, you can. So that means if you really want A dot to be objective, then A has to be special. So if we work it out, for example, let's
Can
see.
we try to work it out, sir?
Yeah. So first of all, we are thinking that A is objective, right?
Okay. A tensor also we can take or a scalar, anything. We can start with say a tensor. A is objective, we are telling, yes.
QA
QA, Q transpose.
transpose. So since A is objective, so A is changing to QAQ transpose. Now, when we look at A dot, Then this is Q dot A Q transpose plus Q
A
A
dot Q transpose.
Q transpose plus Q A Q transpose dot. So if we want this to be objective, these two together must be 0, right?
These two together must be 0, correct.
So how is that possible?
Yeah, I was trying to figure it out.
One of the possibilities is that A is diagonal. If you make A proportional to identity, okay, say A equals to some alpha times identity. So in that case, we will have alpha Q dot Q transpose from here, and from here you will have plus alpha Q dot transpose, which is equal to alpha Q transpose whole dot, right? Which is alpha times identity dot, which is actually 0.
Okay.
So if you have A proportional to identity, then indeed in that case A dot, in this case A dot is indeed transforming to QA dot Q transpose, and then it becomes objective.
Okay.
Yeah, I don't think there's any other situation other than this.
And how to work out by working in forward direction only, like we substituted alpha and we have worked out. Is it possible that two terms somehow we can try to combine? Because it is having one in Q dot in left side, another is having Q dot in right side.
That's true.
But this is also fine. I guess.
Other one is so this is same as Q dot A transpose Q transpose whole transpose, right? So that implies the two things together is Q dot A Q transpose plus Q dot A transpose Q transpose whole transpose, and we want this to be G.
Then A is equals to A transpose. We have to take like one.
Yeah, one.
Will
So
come from
say
here.
that let us suppose A is symmetric. So if we suppose that A is symmetric, then we have.
Then that tensor has to be skew symmetric. Q dot A into Q transpose.
Yeah, it has to be skew symmetric. So what does it tell about the symmetric A then? So say A is symmetric.
And also we know Q dot into Q transpose is skew symmetric. So
Yeah.
again, we have to think that A can be identity so that these two are anti-symmetric.
Right, but I was just thinking, is there some more general A possible? So Q dot A Q transpose must be symmetric. So what can we say then? And Q is a general Q.
Q is general, yes.
So maybe we write it as Q dot Q transpose into QA Q transpose. Which is some W antisymmetric times QA Q transpose, which is symmetric. So we
Because
want
all three are okay.
Yeah,
QAQ transpose symmetric, how will tell sir? A is symmetric.
Yeah, that is why if you take the transpose, you get the same thing.
Oh, okay, okay.
Yeah. So antisymmetric times symmetric, and we want this to be symmetric.
No, we want this to be antisymmetric only. Total
Yeah,
thing should be antisymmetric.
right. It must be antisymmetric. So it must be antisymmetric. So antisymmetric times symmetric tensor, giving you antisymmetric tensor. That's of course, if A is proportional to identity, then it is, you can see it is. I think maybe there is some more general A, but right now I'm unable to think of how to figure out if it is at all possible. Yeah. Okay.
And also,
But,
next.
Hmm.
So, what is the main difference between this convecting and co-rotating basis? Because after reading what I understood is co-rotating is like special case of convecting only, no? Where the
Yeah.
L becomes W. So then.
Well, see, the convecting is, when you say convecting basis, then it is the basis vectors are actually attached with the material, right? And if that is the case, then they will really flow with the body. And then you can indeed say that F dot is equal to L times F, isn't it?
Yes, sir.
So that's convecting basis. And co-rotating basis, those bases, these basis vectors are not attached with the body. If it were attached with the body, then it would have been convecting basis. They are not attached with the body, but they are just spinning with the body. So it's like an imaginary basis which is spinning at the same rate as the body. So that is all we can say. And
Spinning means that
therefore,
only rotation. Then, if the body is translating, then that basis vectors will remain same.
yeah. Well, yeah, exactly. If body is translating, then its spin is 0, then the basis vectors will remain same. Yes.
But here, sir, if we make L equals to D plus W, like L if we replace with W, where
Yes.
the that strain part is 0, so then we get the convecting like co-rotating basis, no? From
Yes. So if
convecting
it's
to
a
co.
rigid body, for rigid body, then if the basis vectors are attached to the, if they are engraved in the rigid body, and then the rigid body is moving, in that case, those basis vectors are indeed co-rotating basis and also co-convecting basis. In that case, it becomes both co-rotating as well as convecting, because L is same as W, so it is both.
And convecting is like a large group of bases, no? I mean, there more thing can come, spin as well as,
Yes.
because their spin also can come. We can think of.
Yeah, of course. And this convecting basis in general, it is, as I had thought earlier, it is such a basis whose not only directions are changing. See, the basis vectors f1, f2, f3, if it is initially perpendicular, it need not remain perpendicular later on. At the same time, their magnitudes are also changing. So it's like it's possible that f1 is getting inflated, f2 is getting compressed, and likewise f3 is undergoing something. So the basis vectors are not only changing angles between them, but also their magnitudes are changing. And then you are measuring things related to such a basis vector. So it's like the scale of measurement is also changing.
Okay.
Yeah.
So it is not a unit based vectors, no? Like
Yeah.
magnitude also is not going to be unit then.
Yeah, right. If it is
And
initially unit vectors, then it need not remain unit vector later on. But in case of co-rotating basis, if it is initially unit vector to begin with, it will remain unit vector. And if also the angles are preserved in case of co-rotating, that is why the name rotating, no?
understood.
Yeah.
There, it is not engraved with the body, the basis
Yes.
vectors.
Yes.
And also, so this F dot equals to L into F we have written.
Yeah.
So normally when we take this L equals to theta F dot into F inverse. So I mean,
Yes.
this how we have written when anything will like its dot product. Normally L will be F dot into F inverse. So I mean here
And
directly basis vectors, how can
this F is not big F. It is not big F.
no, that I understood, but how it is arrived at, because line element it is changing in this way, no? Lambda dot by
Yes.
lambda equals to dny dot ny.
No, even for a not just for the magnitude of a line element, but also the line element itself. We had derived earlier that line elements indeed their material time derivative is indeed this.
I might have
So
mistake.
we know that dy is equal to f dx, right? This is how line elements transform, small line elements.
Correct, correct.
So if I take time derivative, then dy dot is f dot dx, right? Which is same as f dot f inverse into f into dx, which
Okay,
is
okay.
L into dy, right? So you can see that line elements, their rate is
But
as
line element as a whole is like changing rate, it's changing very simply. But when we think of its orientation, we had a very difficult formula, no? I mean,
yes, of course.
but here
But
orientation also is covered. So
yes, here both are covered, both orientation and magnitude together. The formula is simpler, and only
oh,
for the magnitude or for the orientation, the formula is not simpler. It's
okay.
possible.
So
Yeah.
like it was not intuitive for me, so I thought that.
Right, right.
Okay.
Okay.
Now, sir, one more thing.
Hmm.
Sir, when we talked about equipresence, so
Yes.
like we have put similar argument in all the variables, like all the functions, basically constitutive functions. So,
Yes.
but when we are removing one by one
Yes.
by putting this second law restrictions or using objectivity
Yes.
restrictions,
Yes.
so can we
Yes.
not remove from all? I mean, equipresence will not work in the other
No,
direction.
because the removal was done in a logical way, no? It was as a mathematical deduction we were trying to remove it. We first saw that I guess psi was not a function of grad theta. That is the first thing we saw. And then because p is derivative of psi, therefore, and psi does not have grad theta, therefore p will also not have grad theta. And similarly, eta was also derivative of psi, and psi does not have grad theta, therefore eta will also not have grad theta. So it was being done mathematically. But for
Yeah.
Q, it was because it was not a derivative of psi, so we could not say that.
Okay. Okay.
Yeah.
And so Q naught, our referential heat flux vector.
Yes.
So that was depending on deformation gradient also. So is it
Yes.
intuitive, sir? Grad theta and theta I can understand. Deformation gradient, how it will depend, sir?
Um.
Q naught, or is it possible to reduce that also? But we might not have worked in class like
Yeah. Of course. I mean, see the Q naught, the general Q naught function had big F,
F theta and grad theta.
grad theta, and theta.
Theta.
And then due to objectivity, we would know that this has to be some
C,
U only, right? U tan,
C or U, huh? Correct.
yeah, C or U and theta. But then you are asking why it should depend on U, right?
Correct, correct, correct.
Yeah, that's a good question. Mathematically, this is what we saw. And physically, why it's so Q naught is related to, I mean, it is heat flux, right? It is giving you the heat flux, referential heat flux.
Correct, sir.
So I guess one of the ways could be, for example, the generalized Fourier law says that Q naught is some second order tensor k times grad theta. right, with a minus sign.
Yes.
So this U dependence you can bring in this K. And then you can say that as the body undergoes deformation, the K would change. But physically,
Yes.
why it should happen, I think one has to go deeper, look at the microstructure, if at all it is happening. And I think if mathematics is allowing it, then physically perhaps also there should be a situation where it should depend on you. And then to come from physics, I think one has to look at the microstructure of the material, the mechanism for heat transfer, and
Yes.
that should give an answer. But right now it is not clear. I mean, I can't give you an exact answer how K can depend on U.
Now, sir, in lecture 30, I guess, yeah, lecture 30, when we were discussing about thermoelastic materials,
Yes,
so you put sigma and then this internal energy Q and eta in left hand side, beginning of the lecture itself, and right hand side we have put first Piola and then psi Helmholtz, specific Helmholtz energy, and Q naught and eta. So whether psi is then has a Lagrangian flavor, but it is like more defined
just a second.
psi.
I'm opening it and then you can comment. So where you're seeing?
The first beginning itself, sir. So here
Yeah.
left hand side, whatever we have written looks like we are trying to define Eulerian type of quantities, and
Correct.
right hand side Lagrangian type of quantities.
Yes. Yes.
So whether psi we have defined it in the Lagrangian, like this specific Helmholtz energy,
Yeah.
it is epsilon minus theta into eta. So it can be in both the configurations, no? Energy psi basically specific Helmholtz
Yeah.
energy.
Yeah.
Is
Yeah.
it a Lagrangian quantity? I mean,
Um. Yeah, you can say that it's a. See, when you say it's a Lagrangian quantity, you have to be clear what you mean. Does it? I mean, we say Lagrangian functions if the arguments are, of the reference configuration. So here, this psi hat, depending on big F theta and grad theta.
so psi hat, can we not think depending on grad y theta?
Well, of course, you can think that way.
Because in lecture 30, sir, I had also found out that we have worked out everything in our Lagrangian frame. I mean, before lecture 30, thermodynamic laws and all we have defined, like we have derived first law, I think we have derived in both, but second law we derived only in Eulerian. And here, while using and introducing psi, we went back to Lagrangian framework.
Okay. But second law, you
Bottom
can
the
also
formulas.
derive in Lagrangian. Second law, you can also derive in Lagrangian framework. And likewise, this reduction can also be done for Eulerian. We just took one of them.
Okay.
Yeah. I just didn't do both of them because it would have taken time.
Yeah, understood, sir.
Yeah.
So, but psi hat can be defined in both.
Yes, of course.
And the motivation of going from this E, like which is the internal energy, to psi
Right.
hat to eliminate basically the Q vector, no?
Well,
Not Q, R actually, that heat source. Rho
well,
into R we are
no,
replacing.
the
So,
motivation, I'll tell you, it is not that. The motivation is when you go to psi hat, no? With psi hat, everything then, it's also there in the book. With psi hat, and then it being dependent on, as we wrote here, F and theta, then you only need psi hat and you can deduce everything else. You just need psi hat, you get P as well as eta. But if you had energy, internal energy, and you use second law of thermodynamics reduction, you won't get just by internal energy, you won't be able to get both P and eta.
Okay, understood.
And but if you want to indeed use internal energy, then you have to think it as let me write here, internal energy being a function of F and eta. Instead of theta, you think of internal energy being a function of eta and grad theta. And with this, then it works perfectly fine. From internal energy, then you can find P as well as temperature. So temperature turns out to be, I think, del E by del eta. So basically, if you are working with functions whose argument is theta, or let us say if you're working in a formulation where theta is the primary variable, then it is easier to work with psi hat. But if you're working in a formulation where eta is the primary variable, then it is easier to work with internal energy.
Okay, okay.
Yeah, I
Understood.
didn't discuss this, but it's there in the book.
Okay, got it.
In inequality questions, there is always we have sign difference in your equation and in book equation.
Yes.
So, so what did you take for that sign difference? Means what assumption that did you take?
You mean for Q naught?
No, sir. In inequality question, there is q dot del x theta upon theta.
Yes.
Everywhere there is plus. Book has written minus sign, so that's problem is here.
Yeah, that's because in the book, the Q naught of book and the Q naught that we did are related by plus minus. Our Q naught that we did in the class is negative of the Q naught in the book.
Why so?
Because you will see that the heat flux in the book is defined as heat flowing into the system, whereas heat flux in our course is defined as heat flowing out of the system. And that is what I think most of you have done in undergraduate, and I didn't want to deviate from that.
Yeah, okay.
Yes, that's the only reason.
Sir, and in lecture 29,
Yes.
can you open, sir?
Okay.
Sir, go to last line.
Last line. Yeah.
Sir, why this inequality change to equality, sir? P cap is equal to rho square.
Oh, see, this inequality is for the whole thing. This is for the whole thing. And rho dot is arbitrary. It can be plus as well as minus. Okay. But this inequality has to hold for all thermodynamic processes where rho dot can be plus as well as minus. It should be always less than equal to 0. So when is this possible? Let us suppose this thing inside the bracket is not 0. It is something. Let us say it is negative. Okay. Then you can think of a thermodynamic process in which rho dot is also negative. And then for that thermodynamic process, the entire thing becomes positive, which will then not satisfy this inequality. Likewise, let us suppose that the thing inside the bracket is positive. Then you can think of a thermodynamic process in which rho dot is also positive. And then this whole thing becomes positive again, which again violates this inequality. So only way that this inequality can be satisfied where rho dot is arbitrary is that the thing inside the bracket must be 0.
Okay.
Yes.
Okay. Sir, and then I3 is equal to determinant of C.
Just a second. Say again.
I3
I3, yes.
is determinant of C.
Yes.
When you differentiate dou I3 by dou C, you
Yes.
get I3 C inverse.
Yes.
And For incompressible material, we have phi c is equal to determinant c minus 1.
Yes,
And when we differentiate dou phi by dou c, we only get c inverse.
because I3 is 1 there, no?
So, but
Determinant is
I3
equal
is
to,
determinant, no?
yes, and that is equal to 1 for incompressible material.
Okay. So,
Yeah.
but when in extensibility, we are doing c e dot e minus 1. When we differentiate that, we got e cross e.
Okay.
And then what will be the n equation? Alpha f e cross e f transpose. I cannot simplify that.
That you work it out, I think. I gave that to you as an exercise.
Sir, constitutive equation, to satisfy constitutive equation, we need three things: on second law inequality, material symmetry, and objectivity.
Yes.
Second law inequality, to satisfy restriction that the universal entropy remains always greater than equal to 0. That should be satisfied. That's why we satisfy the second law inequality.
Yes.
And thing objectivity, one can choose different reference frame to measure the deformation in current configuration.
Yeah.
That's why if every configuration, irrespective of choosing 1% configuration, that should be constitutive equation should be satisfied. That's why objectivity should satisfy. I'm correct, sir?
Yes. Yes.
And for material symmetry also, one may choose different reference frame starting with. That is why material symmetry also satisfied. And likewise, as
So,
visual
but material symmetry is not for any reference frame. See, the idea was there are materials. I mean, we saw now that the response function, the final Cauchy stress is only depending on the current configuration. But then, because it's a function of big F, and big F depends on reference configuration, so the response function, the formula of the response function should also depend on the reference configuration because it has big F in it, and the outcome should be independent. So therefore sigma hat, that function, should depend on the reference configuration. But then due to microstructure of the body, it is possible that that function is same in two related, in two different reference configurations, but not for every reference configuration, in only for certain sets of reference configuration.
actually, I'm telling that sets of reference configuration.
Yeah, so you have to just restrict to only for those sets of reference configuration, not for all reference configuration for material symmetry. Whereas for objectivity, it can be any of them. It can be any. It can be any related through Q, but for symmetry, it can't be any. So that's the only restriction.
That's why we have to specify the which reference configuration we start there.
Of course, that is also there, that the symmetry, but also, and there are two things: which reference with respect to which reference configuration we are talking of symmetry, and also even for a given reference configuration, it can't be all other equivalent reference configurations. It is only some restricted, and that's because symmetry depends on the microstructure of the body. For example, the crystal lattice, cubic or orthorhombic or whatever, or what's the type of grain boundary? Is it randomly distributed at micro scale? So all on those things, the set of reference configuration depends on those things. Basically, I mean, for symmetry, the set of reference configurations are restricted and it forms that group. Whereas for objectivity, we have to ensure it for all equivalent reference configurations which are related through Q, for all possible Q.
Yes, sir.
Yeah. I'll just add to it that there are some quantities which indeed depends on reference configuration. For example, Piola-Kirchhoff stress tensor. It indeed depends on reference configuration. If you change the reference configuration, you really get different P. Although it is related with sigma, but you know that how P and sigma are related. For example, P is I think J times sigma times F inverse transpose, perhaps. And you can see that it has J as well as F, which depends on the reference configuration, choice of it. So therefore, P is indeed dependent on the reference configuration, but we can't say that for sigma. Likewise, the strain, this big C, for example, it is dependent on the reference configuration because we measure deformation relative to the reference configuration. So there are quantities which, because of the way they are defined, they depend on the choice of reference configuration. So for such quantities, we cannot say that they should be independent of reference configuration. But the quantities which truly depend on only the current configuration, for example, density or the Cauchy stress tensor. So they should, for them, this objectivity is kind of what Nilesh is saying, or Niladri perhaps, yeah, that such quantities should not depend on what reference configuration I choose.
In quiz 2 solution, actually, that last question, 15 number question, there is one operation where I had some doubt.
Are you able to see it now?
Yes, sir. Yes, sir.
Okay. Yeah, tell me.
There, like, sir, this operation which we did, like P double contraction omega F plus RU dot. After that, like we took out F transpose on the right hand side. And we took out like this R transpose on the left hand side of P.
Yes.
So is this any like method to do this, or like
yeah, you can show it using indicial notation that it will indeed come out this way.
Okay. So in exams we can directly write this step, or do we need to show like?
No, you can do it. If yeah, I think you can directly do it. Yes, you don't have to show it.
Okay, sir.
And the proof, you can do it through indicial notation, that indeed if you bring the matrices on the other side, it comes with a transpose.
And sir, in question number 5, the uniaxial loading like matrix was there.
But be very careful. You also have to be careful about where you put the matrix. For example, you see this big F, when I brought it on the other side of double contraction, it came after P.
Yes, sir.
Not before P, because on the other side it was after omega, no? Therefore, yes, when you bring it on the other side, it must come after P. Similarly, this big R, it was before U dot on the other side. So when you bring it on the other side of double contraction, it must come before P. And transpose always happens.
Yes, sir. And sir, like I was trying to do by using left hand side. So like the expression for U is under root F transpose F.
Yeah.
Now, like if we differentiate U square, so like I was getting U dot equal to 1 by 2. Then there was the differential term in F. I think F dot transpose F plus F.
But you see, that is it's not simple to. I think you are just applying the rules, assuming it's a scalar quantity, no?
Yeah, because sir, I was facing problem on like on which side should I multiply with U inverse.
So what you're saying is U is F transpose F half. So U dot should be half of F transpose F, then minus half, and then doing this. Is that what you're saying?
Yes, sir.
But I'm not sure if you can do that.
Yes, sir. Actually, main problem was like on which side you should, like U inverse should be multiplied.
Or also, where should this go? Should this go on this side or it should go on the other side?
Yes, sir. Yes, sir. That one is the U inverse one. Yes, sir.
Yes. So you can't do that. Yeah.
Okay, sir. Answering question number 5, actually.
Yes.
For the UniXL loading, like we got the diagonal matrix. So that
Yes.
I can understand that we will get the diagonal matrix. But
Yes.
all the elements were same in the solution.
No, it
So-
were not same. It was cross. Cross does not mean it's the same.
Okay, I thought that like it is written X. So like similar but
Cross
unknown.
is unknown, so they are all three unknowns. It's not the same.
Okay, sir.
Yeah.
So psi, which is a function of theta, grad of theta, and f. In 30 lecture,
Yeah. Tell me.
psi was taken as function of f, theta, and grad of theta.
Yes.
But in the 31st lecture, it was only taken that it is a function of f and theta.
Yeah.
Sir, why grad of theta was not taken there?
Yeah, because we actually proved it in the lecture, no, that dependence on grad theta is gone. Maybe Vishwas, can you tell me which lecture it is?
Lecture 30.
That is in 30, sir. 30.
Lecture 30. Okay. So there I have proved it that we started with dependence on grad theta, but then we could show that psi should not depend on grad theta. But in the beginning, we did not know whether it will depend or not. Therefore, we started with the general function. And why did we choose grad theta? Because we knew from physics that heat flux depends on grad theta. And then applying equipresence, we brought it everywhere. But then we started doing mathematics. We saw that, okay, psi should not depend on grad theta. So I think, let me see where it is.
Little down, sir. Little down.
Little down, okay.
Del psi by del g. Little
Yeah,
down, sir.
exactly.
Del
Yeah.
psi by del g somewhere.
Right.
Yeah, this one.
You see, this is what we got here, no? And how did we get this? Let's see.
From that inequality, sir, top, like it can be chosen arbitrarily. That g dot can be chosen arbitrarily.
Oh, yes. So in the inequality, you have, look, you have this term also, no? And because g dot can be chosen arbitrarily, f dot, theta dot, g dot, they all can be chosen arbitrarily. Therefore, their coefficients must vanish. And that's how we see that del psi by del g must be equal to 0. So psi must be independent of g, which is grad theta. Akasip, is that okay?
Yes, sir. Yes, sir.
All right.
Sir, like here we chose that rho naught. Yes, sir. We chose this one. F dot is equal to alpha times rho naught into del psi by del f minus p.
Yes.
And other two time derivatives as 0.
Yes.
And we derived for the expression for p.
Yes.
But we chose a particular thing and derived p. Is it valid everywhere?
It is valid everywhere. Yes. It is. See, all that we are saying is that the coefficient is vanishing. So see, because it has to hold for every, this inequality has to hold for all the processes. So you can apply each specific cases and reduce something. So by choosing f dot equal to this, you got this. and this will then hold. Similarly, you can choose f dot to be something else, and if you can derive something else, then that is also going to hold all the time.
Yes, so that's what I was asking. Then we can choose other combination and also derive some other expression.
If possible, yes, of course.
Sir,
Yeah.
I had a question like before the test part, the traction vector part. Sir, we know that the traction vector at any given position at any time is arbitrarily oriented surface element, like which is characterized by the unit normal vector n, right? Sir, how could we figure out the maximum and the minimum in those cases? Like, what is the maximum traction along which orientation and the minimum traction along which orientation, or probably
Oh,
the
okay.
shared traction as well?
Are you asking? Let me see what you're asking. So what you're
Sir, I'm
saying is
basically
that, yeah, I got, perhaps I got it. I
asking
just,
about
what you're saying is that if you have a body and at a point you choose a normal, you find some traction. Then you choose another normal, you find another traction. Then you choose another normal, and you get another traction, right?
yes, sir.
So you're asking on which plane it will be maximum
And minimum.
and minimum.
Yeah.
At a point, right?
Yes,
So
sir.
that is, that is what we say. Now you can't say maximizing or minimizing the traction. You can say, for example, maximizing the magnitude of traction, or let us say maximizing the normal component of traction, or maximizing the shear component of traction.
Yes, sir. Exactly that.
Yes. So this is something it is done in undergraduate class, and if you have not seen it, then I will send you some material that I have. I have
Thank you so
derived it
much.
very nicely. So please send me an email, okay?
Okay,
And
sir.
I will send you the relevant material.
That'll be helpful. Thank you.
Yes, thanks.
This when we have worked out our lecture 35, I think the last lecture, thermoelasticity,
Yes.
linearized theory of thermoelasticity. Can you open it?
Yeah.
So here, so initially for linearizing this grad x of p, so we have linearized to 2 rho naught del psi by del c. So that middle of this page we can see 2 rho naught del psi by del c, plus higher order terms. So this is what we have linearized. So with this way, the same equation giving us only one linear component, which is like understood also because del psi by del c will be minimum linear. So anything order will be minimum like linear in u or grad u or u maybe. So when we multiply it by anything
I
of u,
I see what where you're going. So actually here, when we are doing it, no, there was a assumption that I mean it was not assumption, but I thought that del psi by del c will not have a constant term. So for example, I thought that there is no residual stress. You can notice that even here, if del psi by del c has some constant term, this can also give you a linear term, no? So that is something I missed here. I know. So while I was doing it, I figured out that I have.
Yeah, exactly. My doubt was that only that gradient of u into s naught is linear, but here we are telling it as non-linear. So
right.
So then psi can be arbitrary, and we actually do not know the degree. I mean that way we can. Order.
It can have constant term. I mean the derivative can have constant term, and psi need not have the quadratic term only to begin with. Psi can have a linear term in C, so that when you take the derivative, you get a constant. Because if there is a residual stress, you should have del psi by del C giving you some constant value. But if there is no residual stress, then del psi by del C should be 0.
Because we can see if del 2 psi by del c2 always should exist, no? Because it is coming in our stiffness
Yes.
expression, that fourth order stiffness tensor.
Correct.
So then from here we can think that psi has to be minimum second order. I think first order psi will not work because it will become 0. Del 2 psi by del C2. If
Yes.
psi is
No, what you are saying is that it must have the second order term also.
correct. Psi function.
Minimum,
Basically.
but what you're saying is psi must have the second order term also. Otherwise, the stiffness will always be 0.
Correct.
Yes. That's true.
Yes. And now one basic mathematics related doubts, sir. Like when we worked out these traces, so everywhere E tensor product E we are writing. So that is like both E and E will be always same only, no? Like, I mean, we need not take two free indices, no?
Where you are
I mean, where these traces we have worked, not in this lecture, sir. Earlier lecture where trace we worked out, no, for our isotropic materials or this transversely isotropic trace when we worked out. So there E tensor product E term is coming.
E being the Green Lagrange, which lecture?
No,
can you tell
not
me?
E, small E. Lecture I will tell.
Lecture
Lecture 33.
Yes. Yeah, E tensor product E, yes, small e, yes.
So that E tensor product E is, so there E and E both will be same only. So it can take EI, is like EI, so I will be going from 1 to 3. So it will finally give us an identity matrix only, no? E
No. Okay, that E tensor product E, you don't have EI tensor product EI. It is just one vector E tensor product E.
Okay, it is only one vector. Both is equal,
Yes.
and both is equal also.
And both are equal also, yes. There is
Okay.
no
And
index there. See, there is no index there which you have to sum.
okay, but it's written in the vector form, so automatically indices will come, no? E vector is written.
Yeah, E vector is written just, there is no index there.
Lecture 33, can you open, sir? 30.
Yeah, sure. Okay.
Take their A vector tensor product with A vector also in case of E.
Just a second, I'm opening it, then you can ask me. Yeah, so
Further down, sir, I4 and all, when we have written the expressions for transversely further down. Here, I4 right side, this page only, sir.
yes.
Say I4 or I5, anything we can take. So here, E tensor product E, what is this E, sir? It can take 1, 2, 3 or?
No, it can't take 1, 2, 3. It is a spatial direction. See, this is that spatial direction E in the material. So what I'm saying is that there can be material which are such that in a given spatial direction, it is inextensible. So it's only that direction. There are not one, there is not another one or another one.
Okay. Then E tensor product E in this case will have only one entry in the matrix. Then.
Yes.
At different locations, maybe.
Exactly.
It can be E1, E2, E2.
If you have written EI tensor product EI, then I understand that there is, see, for applying summation, there has to be an index, no? But there is no index here. So how can you do summation?
But it's written in the vector, so it is intuitive like.
No. Why?
Understood. Yeah.
Yes. Whether it is a vector or a tensor or whatever, if there is no index, that means there is no summation.
Understood. Okay.
Yeah.
All such cases, then it is a one direction only, and
yes,
one entry.
Exactly. It's just one direction.
Okay, sir. Yeah, and one more thing, sir. So, lectures. Lecture 33, can you open, sir? 33.
Yes, we have opened it.
Lecture 33 only, yes. So here, when psi above, sir, like beginning itself, beginning.
Yeah.
When material isotropy we have applied, so like when F changes to FQ, basically for material isotropy, F changes to FQ. So C will be changing to QCQ transpose.
Correct.
And our previous lectures, actually, we have used Q transpose CQ, but both is symmetric, so I think we can use interchangeably, no? Just as a clarification. Previous lecture.
Yeah, right. So that's a good question. Actually, we should have written it Q transpose CQ, but we use
this full lecture we have followed this.
See, we should have kept, we should have written it Q transpose CQ to be rigorous, but QCQ is also fine, because if Q is in the symmetry group, it turns out Q transpose will also be in the symmetry group. So you can think of F changing to FQ transpose, and then C will then change to QCQ transpose. So this is perfectly fine that way also. But to regress,
otherwise, even
Q transpose CQ.
Otherwise, this QCQ transpose also, it is like transpose of Q transpose CQ. And C is symmetric here, and Q transpose.
No, transpose of it is same as QCQ transpose, because it's already symmetric, so its transpose will be the same.
Yeah, I think with that logic, then only we have to tell.
Yeah.
Q transpose is also in the symmetric. Okay.
Correct. But basically, what I'm saying is, if Q is in the symmetric group, then Q transpose will also be in the symmetric group, because, and of course I haven't told you why, but it forms a group, which is a formal term in mathematics, and they are closed. The groups are closed. When you multiply two members of a group, what you get is also must be in the group itself. And identity is always in the group. So if Q is in the group, Q transpose must also be in the group, because Q into Q transpose is giving you identity. So and you can get here by applying Q transpose, right?
Okay, understood.
Yeah.
Thank you.
Yeah, so for purely mechanical motion,
yes,
you said that the Cauchy stress and psi will depend on J only. So, sir, how is that? Why is it not depending on F?
I said on F only. I didn't say on J.
Compressible, you choose J.
For purely compressible, we choose J. Then we derived it till F, sir. Like J, we have reduced it till that F.
Say again, what you're saying?
Or compressibility and incompressibility factor depends on J. That's why you choose there J.
Well, that was. Are you talking of the example that we did for the compressible fluid? I guess. See, in general, for a compressible material also,
yeah, sir.
the psi will not only depend on J. If it's a isotropic compressible material, for example, it depends on all the three invariants, I1, I2, I3. It need not depend just on I3. I think we did an example of compressible fluid where we said that it only depends on J. So that was a special case. It turns out for a fluid, you can actually deduce it that its symmetry group is all H, such that determinant of H is equal to plus minus 1. Its symmetry group is the entire unimodular group for a fluid. And for such material, I mean for fluid, then if its symmetry group is entire H, such that that is equal to plus minus 1, then it turns out it will only depend on that third invariant. The first and second invariant dependence goes away, and it only depends on third invariant. So that you can show mathematically. So that was a special case. It's not always the case.
Okay, sir.
Yeah.
And sir, in lecture 31.
Yeah. Yeah, tell me. Are you there, Devans? I can't hear you.
Yeah. Sir, for the first part, while separating the variables, we
Yeah.
separated it in terms of F, like D side df, dow side df, double
Yes.
contraction F dot.
Yes.
But
Yes.
when we are doing it again, we are doing it in terms of C. Is there
Exactly.
any reason for it, or it's just
Yeah.
for the mathematical
There was a reason because
ease of mathematics?
see, initially we did it with F so that we could cancel things. No. I think things are getting cancelled when we initially started with F. Let me see where it is.
Yeah, so it's just for the ease of mathematical
Yeah,
calculation,
ease
right?
of mathematics. Yes, exactly. Because you see, this thing and
Okay.
this thing are cancelling. It could have been done only if we start with F, but you could have also done with C. See, even if you start with C, then you can show using some calculation that del psi by del C double contraction C dot. If you had started with C, you would have del psi by del C double contraction C dot, right? And then you could have showed that that will be equal to this through some mathematics, and then you could have cancelled again.
Okay, sir. And
Yeah.
sir, for in the LMB, like in the box, will it not be J into B?
Yes, you're right. It will be J into B. Thank you. Yes.
So the right stretch tensor is not objective, right?
Correct. That is correct.
Sir, in lecture 29.
Yeah. Yeah, please go ahead. I'm opening in the meantime.
There is a mechanical motion, purely mechanical motion.
Yeah.
And unknowns are rho, V, Cauchy stress tensor, and Helmholtz function.
Yes.
That's the unknown. And we
Yes.
can constitutive equation, Cauchy stress tensor, and Helmholtz function.
Yes.
Right. And after that, the equation will be equation 4 unknown.
Correct.
Then when we go for constitutive equation for Cauchy stress tensor, the arguments would be rho and F. If we apply compressible inviscous fluid there, then we apply the argument J, because here rho and J both are dependent. That's why we argument there only J. And compressibility and incompressibility also depends on J.
See, let me tell you. So yeah, so we said that sigma and psi are things for which we want constitutive equation. But then saying that it only depends on J, it's we did not, no, we had no logic to say why it only depends on J. We just took a, we just said that, okay, let us assume it just depends on J. And it turns out, like I was saying earlier, it turns out that for compressible inviscid fluid, indeed, sigma only depends on J. And that you can prove by using symmetry argument. For fluid bodies, the symmetry group is all H, such that delta H is equal to plus minus 1. And then you can do some mathematics to show that it will only depend on J. But we did not do that here. We directly said, let us assume sigma just depends on J and psi just depends on J. Okay.
And rho also depends on J. That's why don't take the rho.
Yeah, that's why later on we changed J to rho, because they are
Yes.
related.
But this is only specific to inviscid, compressible
Yes.
inviscid fluid, no?
Exactly. It is specific to compressible inviscid fluid.
next lecture we have worked out in more general by taking f theta grad theta and then deriving it like.
Yes. Yeah, Manoj.
Yes, sir. While deriving LMB or like other equations,
Yes.
whenever we were converting to dref,
Yeah.
so there we were like taking the dy dt inside,
Yes.
because like dref is constant, so
Yes.
it is time independent.
Yes.
But sir, in the next step, like we were writing, when we were writing the differential, so we were not assuming, like we were not completely expanding it. Like that is what I thought, sir. Like for example, in lecture 19, sir.
Okay,
there
let
is
me
one
open it.
instance.
Yeah, tell me where.
So can we go down, please? Just after we derived like sigma n dA y equal to del y dot sigma. I think, sir, it is in 20 then.
20? Okay.
Yes, sir. I think in second page it will be there. Integration part. Yes,
You
sir.
mean
Here
here?
we are taking this time inside this, like where you have shown the arrow going down.
Yes.
After that, sir, like we wrote d by dt of rho v z plus rho v z dot. Up to that, it's fine. But after that, like we did not expand this like rho v d by dt.
Like which one you're saying?
Sir, like
You're fine here? Are you fine here?
no, sir, above, just above that, sir.
So you're fine here.
Yes.
So after this, what I
Yeah,
have
after
done?
that also I'm fine, sir. Like after that,
Okay.
when we were expanding it, so we wrote rho dot v plus
Yeah.
rho v dot.
Correct.
But we did not write the gradient part. Like
No, so this v dot here is the material time derivative.
okay.
Likewise, this rho dot is the material time derivative. Although the function is Eulerian, but we are doing material time derivative. So you could have written it as del rho del t plus grad rho dot v. So this rho dot is this.
Okay, so here we are assuming like this is the, like we are telling that this is the material time derivative. Okay.
Yes, yes, exactly. It's a material time derivative.
Okay, sir.
Sir,
Yeah.
in the same lecture, in the initial discussion, you said that b was a function of y and t, but then you said that the dependence on t wasn't explicit. Could you please explain it once more? Probably missed it at that time.
Here you are
Body
saying
force, the dependence
function
on
of
body
y and
force,
t.
you said that it was, yeah, that part.
No, b can also depend explicitly on t.
Okay,
I
but then
think I said that in the context of gravitational forces,
okay,
that t is actually only dependent on y and does not depend on t explicitly. That was only for gravitational type of body forces.
so there is no dependence of time whatsoever in regards to body force when we're talking about gravitational forces.
Well,
There
time
is
is
just
because y is changing with time, so implicitly there is a dependence on time, but not explicitly. But also, you know, if you have so this see also it also depends on how you are measuring y. Suppose you have Earth and Moon as closed system, both are moving, right? If you choose
right.
your if you fix your frame at the center of the Earth, then you are measuring everything related to the Earth. But if you fix your frame neither on Earth nor on Moon, somewhere else, then the Earth is also moving, right? Earth has its own motion, and that will kind
Right.
of bring in the dependence on time, I guess. I guess that can bring some dependence on time. because the y will be measured from the origin of the coordinate system, and Earth has its own motion. So yeah, there it can have a function. So see, what I'm saying is, so if you have Earth and Moon, and supposing you have fixed your coordinate system here, then you're measuring y from this coordinate system. But the gravitational pull, that depends on this, right? And say this is ye. Then in the gravitational pull, it will be y minus ye, right? This vector will be there. But ye is a function of time because Earth is moving, Earth is undergoing its own motion.
Fine. Sir, do you have an example where B will explicitly depend upon time? General example. Like in this case, it implicitly depends upon time. Is there an example?
In this case also, ye. See, ye is not our unknown. Our unknown is y. Ye is the motion of the Earth, which we can say that it is known to us. Earth is having its own motion, and we are trying to analyze motion of the Moon. So if ye is known, then you can see that it's then an explicit dependence on time.
All right, because we changed the frame and it brought it outside of both the Earth and Moon. Okay, thank you. I got it.
Yes. But otherwise also you can think of some other body forces. For example, if you really have an oscillator type body force, say for example you have a body and there's a spring and you have some mechanism to vibrate here, forcing this vibration, then this spring is going to exert some force on the body, which will be, let us say, k times x, and x is then a function of time. Now this xt is forced by the external agent. So you can see that here the force is explicitly dependent on time because of, and it is in the way the external agent is forcing the oscillator. Yeah.
Fine, sir. I got it. Thank you.
Okay.
Sir, in lecture 35, we talked about linearizing energy equation. Can we get a bit of insight into that?
Yeah, of course. I mean, you have the energy equation. You think of linearizing in the way we have done LMB, right? You have
The same procedure, sir.
Sorry?
Using the same procedure, kind of the LMB
Yes,
one
using
that we
similar
used.
procedure, yes. Because you have the constitutive function, you can write entropy in terms of constitutive function, then you have to expand the constitutive function del psi by del theta, you have to expand just like you did for del psi by del c, and you'll have first order term, second order term, you'll have some stiffness thing coming up there. Similarly, you have this heat flux Q naught, for which you will have some constitutive function, and that you then again expand. Right? So, and it's a very relevant question as far as the exam goes. Okay, so I think it was a very good session. I'm so glad you asked me so many questions, and we can have another one like Toiba was asking. We can have another one. You can let me know when you want to have it, but there should be enough students. If there's just one student, then we can have one-on-one interaction. And I hope you got something from this course, which you can then apply in your, in your courses for masters or for PhD. Okay, and it was very good to have all of you in the course. And I myself learned a lot of things while teaching the course. Okay, so thank you everyone.